So 6.3 IM1, there are 4 boxes for us to talk about today. The topic is comparing linear versus exponential functions. So something that we should be pretty good at this stage of the game. So the only thing I want to remind you about in box number 1 is that linear functions are represented by a line, and we have used this form to represent a linear function in the past. The m, of course, represents your slope, and of course your b represents your y-intercept. So keep that in mind for this section. Exponential functions, they look like this. They have more of a curve to them, and we know that they can be modeled using the standard form y is equal to a times b to the x, where a is your initial amount, and then b is the number that you are raising the base or your multiplier by. So that's your multiplier. Okay, so just keep in mind that these are the 2 types of functions that we will be comparing today, and we have seen both of them before. So in box number 2, it wants us to plot the points and tell whether the points appear to represent a linear function or an exponential function or neither. So for part A, it says 3, -1. So 3, -1, that point would be down there. And then it says 2, 1, that point would be here. And it says 0, 1, that point would be there. And then it says 1, 3, that point would be there. And then -1, -1. Well, if I connect these, you can see that these do not make a line, and they do not make a exponential curve. So I would say that this one represents neither, because that doesn't match up with anything that we've been working with so far with linear or exponential. B says 0, 1. Okay, that point is here, 0, 1. Then it says 2, -2. So 2, -2 is down here. Then it says 4, -5. So 4, -5 is this point down here, which is kind of hard to see because my graph is down here. Okay. Then it says -2, 4. So that point is way up there. And then -4, 7. So if I drew this correctly, if I draw that, then that definitely makes a line. So I would say this is linear. So far we've seen neither linear. Let's try part C. 0, 2, that point would be there. 1, 1, that point would be there. 2, 1/2, so right there. -2, 8, that point would be there. And then -1, 4, that point would be there. So I would tend to think that this is exponential. And one way we can check that is moving from this point to this point to this point to this point. You can see that this is 4 units, this is 2 units, this is 1 unit, and this is 1/2. So therefore, because I am decreasing by the constant factor of a half, this represents exponential. Okay, so A was neither, B was linear, and C was exponential. Okay, box number 3 is the difference and the ratios of functions. So the idea here is that linear functions have a difference of consecutive y values and that they are constant. So if it's a linear function, the difference of consecutive y values is going to be constant. And if it's an exponential function, then consecutive y values are going to have a common ratio. It says in each case, the differences of consecutive x values needs to also be constant as well. So how do we take all this information and put it into something that we can use? So let's do example 2 here together, using the differences or the ratios to identify a function. So tell whether this thing either is linear, exponential, and then write the function that becomes of it, okay? So let's do part A together. It says here, so I'm going from -2 to -1. That's a +1 difference. Moving along, that's a +1 difference from -1 to 0. From 0 to 1, that's a +1 difference. From 1 to 2, that's a +1 difference. So the difference of consecutive x values needs to be constant. That's what that means. So right now, so far in this example, it is constant. Now, how do I get from 9 to 5? Well, I just subtract 4. How do I get from 5 to 1? Again, I subtract 4. From 1 to -3, I subtract 4. And then from -3 to -7, again, I subtract 4. So the difference is the word that we're doing here because we're subtracting, of consecutive y values is constant. So part A is a linear function. And then it says to write the function. So we can start by saying y is equal to mx plus b. The slope in this case is -4 because it's -4 divided by my 1. Remember, that's changing y over changing x. So -4x. And my y-intercept is a +1 because right here it says when x is 0, y is 1. So this is the function -4x plus 1. And that's what we're looking for in part A. Part B. Let's see here, I'll do it in a different color for you, so we'll go purple. So from -3 to -2, again, I'm adding 1. I'm adding 1 from here to here, adding 1, and then again adding 1. So this is holding, right? The difference of consecutive x values is constant. Okay, now to go from 1/3 to 1, I would multiply by 3. To go from 1 to 3, I would multiply by 3. From 3 to 9, I would multiply by 3, and then again multiply by 3. So this is saying consecutive y values have a common ratio. What that means is if I pick any two, like 27 and 9, these are consecutive, and I divide them, I will always have a constant number. So this is going to be exponential. Okay, so we can start off by saying y is equal to a times b raised to the x. A is the initial amount. And we can see that here, our initial amount, 0, 9. So I'm starting with 9. So y is going to be equal 9. B is going to be that ratio that we were raising. So 3, and then raised to the x. So this represents our exponential function for part B. And that's how we do everything in that third box. Okay, lastly here in box 4, it's asking us to solve real-life problems. And in this case, we're going to use some technology to help us out and show you how to do it. So in 2000, Littleton had a population of 11,510 people. Littleton's population increased by 600 people every single year. In 2000, Tinyville had a population of 10,000 people. Tinyville's population increased by 10% each year. Okay, so what we have is two separate towns. So let's talk about Littletown first. Or sorry, Littleton. I thought I said Littletown. So Littleton. So it says, so in 2000, so Littleton in the year 2000, okay? It says that the population is increasing by 600 and it had an initial population of 11,510. So this is going to be a linear function. Y is equal to mx plus b. The reason I know it's a linear function is it says it increased by 600 people each year. That is a constant rate. So therefore, y is going to equal, our slope is 600, x, and then plus the original amount, which we had was 11,510. So this equation is a linear equation. It represents Littleton. Now let's talk about Tinyville. Tinyville. So Tinyville in 2000, again in the year 2000. I don't have to have a comma there. So the population was 10,000 and it increased by 10% each year. So it's increasing 10% over itself. So we can say this is going to be exponential. So a times 1 plus r raised to the t. Remember, this is our growth rate since we know that the population is increasing. So our initial amount is going to be 10,000 people. Okay, and then there's going to be 1 plus, the rate is 10% expressed as a decimal. So 10% expressed as a decimal is 0.1, and then raised to the power of t. So therefore, I'm going to get 10,000 times 1.1 raised to the power of t. So these are my two functions that I'm working with, okay? And it doesn't say it in here, but part A, or the thing that it wants us to figure out is, I didn't write it down here, when, in what year, what year will they be the same? So in this particular case, right, we're trying to figure out, we've identified a linear function, we've identified an exponential function. We want to know when they are equal, when they are set equal to each other. So I'm going to use some help for this one. So I'm going to show you guys what I did. Okay, let's make it a little bit bigger here and zoom it for you. So let me scoot over. So what I did was I wrote in each one of these equations. So 600x plus 11, 510, and then 10,000 times 1.1. And what I'm looking for here on the graph, x represents years, y represents population. I am looking for where they intersect. So when x is 3, the population is going to be 13,310. So when x is equal to 3 years, and remember, we're doing 3 years after the year 2000. So therefore, we're thinking 2003 is when they will match up, and the population will be 13,310. So that's what we're looking for, and that's how we're comparing linear and exponential functions together and using them to help us sort of solve some problems that we're looking for in real life. All right, that's everything you need for 6.3.